What is the nature of the study of coins? I'm kicking myself the entire time. Osteology. I should know. I kept on going. I knew.
Oh, we are 17. I mean, I'm older, but fantastic. Shall we make a start? Yeah, you want to go home. I want to go home. Yeah. Okay, most wonderful good afternoon to our second session today. And in this second session, I want to firstly actually show you how you don't have to do all these calculations by hand. No, we can do that in a more clever way. With Excel, you are all familiar with Excel? Yeah. You know how to do these calculations with Excel? No. Ah, fantastic, good. And then we have a little bit, we look at how we can visualize the data, just to get an idea of what it might look like. We look at outliers. What if something is really weird? Is it weird? If we've got time, we might even have a chat how we can deal with missing data, although I was just informed that usually if you have got missing data in a clinical trial, you just simply say, we kill that patient. And I mean, not literally, but just remove that patient from the record. That's probably the easiest way. But if you do that with, if you've got 500 patients enrolled and you do that with 499 where something is missing, then you are left with one patient, and it's probably not very representative. And then at the end, I want to quickly show you how you can do all that stuff in this programming language in R. Okay, so how can we do all these calculations? Not just by hand, because if you've got 100 data or so, then it gets a little bit tedious. Let's assume we have sort of an Excel spreadsheet, A, B, C, 1, 2, 3, 4, 5. These are our sort of our columns and row, and you've got data here, something like that. If you want to calculate the mean, that's very simple, although it depends on whether you've got Windows or Apple. I show you the one that works every time. If you want to calculate the mean, all you say is equal sign. That symbolizes that a calculation happens. Then you enter the word average. And in parentheses, your data set. So here we might have from A1 to A5. Yeah, parentheses closed, and it will spit out the mean. Ta-dum. In Windows, you can also do that with the word mean instead of average, but Excel and Mac doesn't know the word mean, which is a bit mean. So I always stick with average because then you can't go wrong. Okay, with median, you can do that. And guess what? The command is median A1 to A5. And it will spit out the median. If you want to do the variance that we have done, you have to be a bit careful. You have to enter VAR for variance. And then it will come up with two options for you. We will discuss the other option, but what I have shown you today is we are just looking at our data. And the correct equation for that would be var.p, A1 to A5. There is a var.s, which we are going to discuss tomorrow, because there is a difference between these two variances. And if you want the standard deviation, you enter STDEV, again, dot P, A1 to A5. So make sure that you enter the P variant for these things. When you just look simply at the data, when you don't do anything else fancy. And something tells me that these commands might be quite useful for one of your assignments. Yeah, you got it? Especially the P ones. Good. Okay, so how can we visualize the data? Well, a very common way of visualizing the data is just simply with a bar chart. What the hell is a bar chart? Let's say we've got 1, 2, 3, 4, 5. What we can do is we just simply plot on the y-axis the mean of the data. And we've got only one data set, so we would just simply say this is our data set here. Data set. And here the mean, we said that is 3. So we could do a nice bar like that. Okay, yeah, that's pretty straightforward. There's nothing special about that. And we can even include the standard deviation. What did we say with the standard deviation? I think the standard deviation was 2. The variance was 2, and the standard deviation was 1.4 or something like that, yeah? Sorry? Root 2, so 1.4. So you can include the standard deviation just simply like that with an error bar, which might look like that. And Excel allows you to do that with a standard deviation. Now, when you do something like that, it is absolutely essential that in the legend of that graph, you explain to the reader what the hell does this error bar actually indicate. And in this case, what you would say is the error bar indicates the standard deviation of the observed data. That makes it absolutely clear. Yeah? There is a very famous paper that unfortunately you cannot read anymore because it has been long retracted from the publisher. What people noticed was that there were some really interesting calculations and data and things like that. And because that person, the author, did not know how to calculate the standard deviations and error bars, what they did was very clever. They did just something like that, yeah, bar graph. And then they thought, oh, well, we need an error bar like that. So what does an error bar look like? Oh, it's like the letter T. So they printed the letter T up here. And the reviewer obviously thought, oh, that's a standard deviation or something like that. But if you look closer, it's just the letter T. Has absolutely nothing to do with reality. It's just the author was too lazy to calculate these things and put a letter T in. That's why this paper got retracted. Well, but it's quite a interesting story. So that is, for example, a simple bar graph. And I would always suggest, and Excel allows you to do these bar graphs and error bars. Always look at your data with these with this visualization. Another very common plot, which I find actually much better than these bar graphs, is what is called, I'll tell you the name later. Okay, let's say we have the numbers 1, 2, 3, 4, 5. God, you must be so sick of this data set, right? But it's easy. Okay, so I've written them down in the order that I want to deal with them. Remind me, what did we say for the median? 3? Yep, let's do that. The median here, right? Now, the median, if you think about it, it divides the data in an lower half and an upper half. Yeah? So 50% of the data are here, 50% are here. That's what the median does. But how about we take the median of the lower half? Do you see what I mean? Yeah? Why not take the median of this part here? Now, of course, we have a little bit of a problem. Should we include this number here, or should we not include this number when we do the median? What do you think? Should we include or should we not include? Yeah? You say yeah. Yeah. Any other views?
Does it depend on whether the median is the middle number or whether it's...
Not necessarily. Actually, you are right and you are not right, because there is no consensus. You can include it, but you don't have to. What you have to do is that you specify what you did, whether you did it or not. And you have to be consistent. You can't go away and say, okay, today is Wednesday, I don't include it. And I only include it for the lower half, but I don't include it for the upper half. So you have to be consistent with it. I quite like the idea of including it. Excel in the normal form, I believe doesn't include it. R does include it. It's a mess. Yeah, but you just simply have to specify. Okay, let's include it. Let's say this is now our data. 1, 2, 3. Can you give me the median of the lower half? 2. Yep, you're right. So that's 2. What's the median of the upper half? 4. Lovely. So, tell you what, because it looks so nice, why don't we connect these numbers? and do a little box around it. Here we've got the median. We've got a box. And that is why this particular plot is called a... It's a box plot. Exactly. Box plot. Sorry?
I'm just mocking him, don't worry.
Oh. A box plot. What do we do with the 1 and the 5? Well, what we could do is we just simply extend our box plot a little bit with a line to the 5 and a line to the 1 here. Yeah? And because that looks like the whiskers of a cat, this is called a box and whisker plot. Not whiskers, that's cat food. It's just the whiskers, right? And this range here, so each sort of part here, this one, this one, this one, and this one, will contain 1/4 of the data. Therefore, a box and whisker plot will divide the data into quartiles. With the same number of data in it. So that here would be the first quartile, second, third, and the fourth quartile. And what we also can do is we can define, change the color, we can define this part here, this red part. So that would be the second quartile and the fourth quartile, if you like, the beginning of the second to the fourth quartile. We can say this distance here has a particular name. Does anyone know what it's called? You are absolutely right. This here is the interquartile range. So in our case, we can say interquartile range. This is usually abbreviated with IQR. Here the interquartile range would be, well, what have we got? We had 4 here, we had 2 here. We can calculate the interquartile range, would be 4 minus 2 equals 2. Yeah? So the interquartile range is 2. And in this interquartile range, if you think about it, there are 1 quartile and 2 quartiles of the data. So 2 quartiles, that's half. So in this interquartile range, we've got exactly 50% of the data located. And then we've got a little bit of, flop to the whisker to the left and a little bit of whisker to the right. So that's the IQR. And we can use that, the IQR, also to indicate a little bit the spread of the data, how spread out are the data. A large interquartile range means, we have a lot of spread out data in our system. Fantastic. So and these box plots, they are very commonly used to visualize data. You can actually plot them either horizontally, like I did, Or you can also plot them vertically, and it would probably look like that. Something like that. You can even put 2 or more of these box plots into one graphic, and you can compare data. They don't have to be symmetric, the whiskers. It depends on the data. And this might be the median. So here we've got the median again. Median, and this one here is also the median. Yeah, that's the sort of the end of the second, the end of the second quartile, the median. And I can tell that, well, these are 2 data sets, and I can say, well, it looks a little bit like the median are different, but the spreads are fairly similar overall. But the distribution of the data is slightly different in these 2 data sets. So that's a very nice visual way of looking at the data and say, oh yeah, that is what the data look like. Sometimes people even include the initial data, something like that. That makes it even more transparent, where you see then that, aha, these are my original data points that gave rise to this box plot. Excel has a nice function that allows you to do this box plot in the graphic thing, in the plots under statistics, that it allows you to do the box plots. Okay, so great. Now, what these box plots also do is they actually allow you to do something that we have been talking about already. You can find outliers in these plots. Now, what on earth is an outlier? Outliers are obviously data points where you say, wait a moment, that doesn't look right. That doesn't sort of follow a trend. Now, of course, you need to have a number of data already where you can say, this is, there's something odd. So, for example, if I say to you, is 34 an outlier? Exactly. No idea. Is 34 an outlier? We have nothing to compare it to. But if I say to you, you've got the data are between 1 and 10, and several numbers, 1, 2, 3, 3.5, something like that. And then I say, is 34 an outlier?
Yes.
Yes, you would say yes. You would. How did you make this decision?
Because if all the other numbers are between 1 and 10, then 34 is the odd one out.
Is the odd one out. Okay. Let's say numbers are between 1 and 10. Yeah? Numbers are between 1 and 10. 34 is an outlier. Good. Okay. What about 27?
It could be.
It could be.
So
you're a bit more careful.
Yes.
Okay. 1 and 10, same scenario. And we measure 11. No. So what we actually need is a sort of a little bit, that was gut feeling, wasn't it?
Yes.
Yeah. What we need is a sort of a way where we say, give me something in terms of numbers that I can say, yes, I can bet the life of my unborn child that this is an outlier, or no, it's not an outlier. And this is where the interquartile range comes into play, because we can use that. And it is a convention, I have to say, only a convention, but generally, if we've got a box plot, like this, here we said that is our IQR. Anything that is larger than 1.5 times the IQR measured from here, and anything that is smaller than 1.5 times IQR measured from here would be considered an outlier. So this dotted line, this is 1.5 times IQR. Now, we had previously, for our data, we've calculated our IQR was, so this point here was 2, this point here was 4. The IQR was 2, if I remember correctly. Yeah. So 1.5 times 2, that is 3. If my maths is correct. Yeah. So we go 3 units in that direction. 2 minus 3, that gives us -1. Right? Yeah? Happy with that? And on the other side, again, we've got 3. So 4 plus 3, that gives us 7. So any number between -1 and +7 is good. They are not outliers. But if we've got, for example, 12, is 12 an outlier in this case? Yes, because it is beyond this 7. I see it actually like a sort of, this is almost like a fence. It's fencing in the numbers that we say, yeah, they're fine, and keeping all the other numbers out. And that is why this thing has also a name. It is called the Tukey fence. The Tukey fence indicates which numbers we consider not outliers, and it gives sort of the boundaries of where we have outliers. And it's very easy to calculate. As I said, it is 1.5 times the IQR. That is sort of this range in there. Now, if we, for example, have the numbers 1, 2, 3, 4, 8. Now let's do 9. We would get exactly this box plot as I drawn it here. So that would be 2, This would be 4. Does it have an outlier? Yeah, which is 9. So this 9 would be located here. So we indicate it here. Here is our outlier. And what about 1? Is 1 an outlier? No? So the 1 would be probably somewhere here. So convention is that in this box plot, I do the whisker only to the last number that is not an outlier. Yeah, only the number that is not an outlier. Should I draw a whisker to the number 9 where the cross is? No. So in this case, we have a sort of a lopsided box and whisker plot with only one whisker in the lower range and no whisker in the other, because the other one, that would be an outlier, and we don't draw that as a whisker. Yeah? So sometimes you see funny whisker plots where you think, wait a moment, Klapper said they should have 2 whiskers. No, that is just simply because there's an outlier. Yeah, makes sense? So we know how we can find outliers. Very simple thing. We can also do sort of, so these are box and whisker plots as a visualization, and it's really nice because we immediately see whether there is an outlier. We can also use, not with a data set like that, but with larger data sets, we can use histograms. You've done histograms? Yeah, of course you have done histograms. Probably not right. But because very often what I see is that the histograms that people try to sell me are actually bar graphs. What's the difference between a histogram and a bar graph? Well, if we have data sets and we have large data sets, we can group the data into what is called bins. It's a little bit like I have like waste paper bins, say 5 bins lined up. The data between 10 and 20 go in the first bin. The data between, well, 20.001 and 30 go into the second bin. The data between 30.0001 and 40 go into the third bin. So I group the data into these different bins or categories, if you like. Yeah? And I draw these bins down here. Here I have the number of data points that I have in there. So count number of data that I measured. And I do the bins. And what you probably see, mind you, the bins don't all have to be the same size. I could have a sort of, this is the last bin, everything that doesn't fit, I just throw in that. And what you see is that typical for a histogram is that there are no gaps between the bins. So the bins are really nicely tight together and there are no gaps. On a bar graph, as I showed you here, where's my bar graph? On a bar graph, I have a gap between things, yeah, between one measurement and the other measurement, or data sets. But with a histogram, you should not have any gaps in between. Okay, so what could that look like? So a typical histogram might, for example, look like that. That's a nice histogram. Yeah? Only worth if you've got lots and lots of data. You very often can choose what bin size you want. The smaller the bin size, the more granular your results are, of course. So if you've got 100 bins, it could very well be that there is one bin that's empty. So you might have an empty space, a gap, but that is not because it is, you know, from the concept, it is just simply there is nothing in it. So think of a histogram just simply as an array of bins that you fill. And if you make these bins incredibly small, you get something like, so we might have something like that. Very often people just simply say, well, we take the middle of the bin and draw a sort of a curve along them. The smaller you make the bins, the smoother your curve gets. Yeah? Very often, this is also a very, very useful thing to see whether what your data actually, again, look like. So what you very often will find, and we will discuss that, I think tomorrow, very often, you will find that you might have data that look like that. Nicely symmetrical. Yeah? There might be lots and lots of bins there that give you that smooth curve. Well, that looks quite nice. These histograms also help you then to see whether the data are a little bit sort of skewed. Could be that there is something weird going on with the data. So, for example, you might see something like that. This is actually what I would expect when you do your assessment. Yeah? Hopefully, most people will get really good marks in the assessment. Okay, there will always a few people who don't get it. That's this tail here. This tail that points in that direction. So these data are left skewed or negative skewed. You could also have data that might look like that. So it's pointing to the right, so that's right skewed. Or positively. This is when you, for example, look at, well, I don't know, life expectancies or something like that. Usually people, die at a certain point, and we all die. But there might be a few people who live really long time, and it might look a little bit like that. Yeah. And this is another important sort of characteristic of your data. It's called skewness. Is it nicely symmetrical, or is it sort of looks a little bit funny, or in that way funny? Yeah. And very often, especially when we work with a particular set of data, we are looking for the skewness. Is there a skew in it? Because then, strictly speaking, we need to, I'll tell you tomorrow what we can't do with these data then, when they are skewed. And I tell you then a nifty trick how we can actually unskew the data. We can use some tricks that make this skewed data actually look like, symmetrical, more or less, again. It's a very dirty trick, and, statisticians hate that when the secrets come out, but it's incredibly useful, this trick. Okay, so these are further characteristics of these parameters. Now, we were talking about the outliers. And, I mean, this could be caused by some outliers here, right? So skewness very often leads to outliers, or outliers lead to skewness. That's the better way around. Okay, what do we do with outliers? You have your data set. You did exactly what I told you. You did a box and whisker plot, and you find, oops, there are some data points outside the two-key fence. By the way, it's two-key, not Turkey. Yeah, no, it's not Turkey, because it's named after a famous statistician, Tukey, who got so fed up with everybody calling him Turkey or gobble, 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 that I think at one point he threw a blackboard. You had these sponges. Mm-hmm. Yeah, blackboard. It wasn't the old version wasn't a rubber. It was a water-soaked sponge with which you erased the chalk on it. And apparently somebody called him Turkey, and he threw this soaking, wet, stinking sponge at that person. I don't know if it's true, but I would not, be surprised. So it's Tukey, not Turkey. And it's skew, not screwed data, okay? Okay, so what do we do with these outliers? Constructive suggestions, please. I know it's close to 4 o'clock on a Monday. What do we do with outliers?
We just ignore it.
We ignore them.
See if you can figure out why they're outliers. Like if it's 580 and it's very clearly meant to be 5.8.
Ah. Mm-hmm. So we've got two options. And Helen, what do you do with outliers in your statistics?
Ask the statistician.
You ask the statistician. That's always a good idea, because then if they screw it up, and that was with an R, if they screw it up, then you're not to blame, right? If the trial goes well, then it's praise to you. If the trial goes badly, then it was the statisticians, right? That's okay. Now it depends on the outlier. So we need to see that a little bit in a differentiated way. If it is just simply a slip of the pen, yeah, you measure blood pressure. Blood pressure is in the range of 80 to say 200 if somebody is totally going ballistic or something like that, and you've recorded a blood pressure of 20,000, then I'm not entirely sure if somebody with a blood pressure of 20,000 will survive the next 10 seconds or so, right? So they are probably not enrolled in this clinical trial. So it is probably a slip of the pen, and it should read perhaps 200. Although I would say if the blood pressure is 200, get them to the hospital ASAP, because you might not have a patient in the trial then. Slip of the pen, just somebody recorded some nonsense or wrote some nonsense. I think we probably safely can say, yeah, just let's ignore that. Yeah, this doesn't make sense. What do you do with a patient? You've got your clinical trial and all of a sudden there's a blood pressure of 20,000 in it. What shall we do with that? Retest, yes, but that was 5 weeks ago, and the patient is now on holiday. What do you do with that?
You'll just have to report it as a non-compliance.
Yes, you could do that. Or in your analysis, you just simply say, we had one weird person. We don't know whether this person even was human. Yeah, so we just ignore them. We take them out of the study. We don't ignore them, we take them out of the study. Yeah, so that person would be probably that person is dead anyway. So the data would be censored in that sense. We take them out. If possible, of course, would be good to retest. Bloody hell, this guy still has a blood pressure of, let's say, 2,000, not 20,000, of 2,000. Jesus Christ, on a motorbike, how is this guy surviving, right? No idea. We retest it. Of course, if that happens, I would probably check the thing with which you measure the blood pressure, because if it shows 2,000, then maybe something is wrong with the protocol or with the measurement or with the device. Yeah, but if you can rule that out and you find something that even when you try to replicate it, what shall you do with it? Well, my advice would be you go away, have a glass of red wine or something like that, if you drink alcohol, and say, wow, that's cool. Let's have a look. Why is that possible? Forget clinical trials. You now go into hardcore research and you grab that person and say, I want to know why you are still standing upright. You should be dead by now, right? And you look at it. If you cannot explain any outliers with that was just a blip or something like that, then you are onto something that potentially is, what's the technical term? Shit hot, right? You see something. That is, for example, how Alexander Fleming discovered antibiotics. He saw that there was mold on the plates, and every logical thinking lab scientist would have thrown the plates away. But he also noticed that where the mold grows, no bacteria grow. Hey, cool. If it was a clinical trial, they would probably said, no, that's, that's not what we are dealing with. Plates go in the bin. He said, that is, whoa, can't explain that. Repeat it, still can't explain it, gets even weirder. We investigate. So that is what you should do with outliers. Think, what is it telling you? Is it something really surprising that's going on? Or is it just a slip of the pen? Now, obviously, the opposite of outliers is missing data in a clinical trial, for example. So you've got 100 patients or 100 participants enrolled, and you want to do a new drug for blood pressure or something like that. And you got all the information, age, height, BMI, cholesterol, God knows what. And of course, your primary endpoint is the blood pressure that you are interested in. And you then see that in, say, 1 or 2 patients, you forgot to record the age. A bit annoying, because what do? Well, as we said, you could omit these people and say we just kick them out of the study, where we don't take them into the analysis, or you can use certain techniques where you try to figure out what could the age have been. So you could, for example, if it's the age, or if it is the primary endpoint, if it's the blood pressure, you could say, well, maybe we just simply calculate the mean of all the others and replace these missing data with, let's say, the mean. It's a brutal method, and in practice, you probably won't do it like that. There are other, more sophisticated methods that you can use to replace missing data. If you ever come across this problem, it's called imputation, not amputation, it's imputation. And there are some techniques available where you say, yes, I've got some missing data. I can make an educated guess what these data might be, and I can put them in so that my data analysis is, again, back on track. Now, if you've got, say, 20,000 patients in a trial, you probably will never come across 20,000 participants. Have you ever? Yes, you have 20,000? And there is one where data are missing. I would say, sort it, right? Who cares? 1 in 20,000. If you've got only 20 people in a trial and you've got 5 people where you have data missing, it's getting a little bit annoying. So, you want to think about, how can I still sort of salvage the trial without having to start from scratch? Obviously, you would have, before you do anything, you would have a data analysis plan, where you say, if this and this happens, then we use this and this method in order to replace data or do something with it. Make sense? Right. So we've done quite a bit, and I suggest we've got about 5-6 minutes break. I know that the smokers are absolutely desperate, right? I can see the slight shake. No. And some people want to stretch. And after that, it will only be about 15 minutes after that. I will show you how we can do some analysis in R. Happy with that?
Thank you.
Good, let's do that.
We're going to do yoga, we're not smoking.
Yeah, you do yoga. Sorry?
Sorry, at least one person smoking.
There's a whole bunch of them. Look, we all die. My wife says to me, don't eat so much. I say, you know, if you eat, you die. If you don't eat, you die. I rather go with my mouth full. Have I made a total tit of myself?
With great. I love this style. Good.
Okay, good, thank you.
I'm happy. I don't know whether this lot are.
Sorry?
I don't know whether this lot are happy, but they're engaged. So good.
Yeah.
I'm gonna have to go and get myself some sugar. Some sweets out of the vending machine, I think. I'm alright, thanks.
You sure?
Yeah.
I have so many more, that's why.
Are you sure?
Yeah.
Thank you very much. Oh, yeah. So careful not dropping on the floor, and I just pushed this crumb off my dress without thinking about it. Right,
You do R?
Not for some time now. Listening back.
Actually, the assessment files that I've sent you, they're all written in R.
Oh, okay.
There is a package that basically compiles whatever number of questions you want, and it just changes the numbers. You just have to put in the question.
Oh, I see. Oh, amazing.
That's
Game changer.
pretty good, yes, absolutely. Yeah. I just deleted it. No, no stress, no stress. The rest is still down there.
Oh, quite late.
Does it make sense what I'm doing?
Yes, no, it's so. I feel like everyone else did maths at A level and I haven't. So this is like a really good catch up. I feel like I'm really getting bored with it. So you're doing a very good job.
Oh, thank you very much.
Also very entertaining, considering stats is.
Stats is not supposed to be entertaining.
Well, you've made it interesting.
Thank you very much. That's very kind of you.
Oh my god. Yeah. That is not good. But crucifixion is not a great way to go on.
Certainly an interesting topic. Yes. Always look on the bright side of life.
Stoning stress also not very nice.
Do you mind, or do I dare to ask what brings this topic?
It's not ants. We're talking about ants.
Yeah, we were talking about ants and like how ants. Still confused. And like, if ants
Crucifying.
if ants kill you, they don't sting you to death. They suffocate you like from inside of you, like they crawl in your mouth and suffocate you that way. And Anna said that's going to be the worst way to go. And we were like, well, you have a start.
Can I, I mean, again, I don't dare to ask, but can I know where you got this knowledge from?
So I got this because in Indiana Jones and the Crystal Skull, there's a guy that gets killed by ants. I was like, is that actually what would happen if ants tried to kill you? And apparently not. Scary stuff.
Yeah.
Still not what I thought it was going to
Where did I just walk into?
There's this guy. Okay, I'm not going to go into that.
Yeah, so-
It was a Japanese guy. Yeah. I'm not going to say it like loudly. You don't want to laugh about this. It's a fictional between the Japanese. Yeah.
How do ants kill you?
Anyway, he was in the rift.
Certainly an interesting conversation.
Like he got kept alive medically for like a month, to the point that he had like no skin left on, no eyelids and everything, but they were still keeping him alive.
Oh, I've seen this.
And his second name was Ouchie, which I just found so
Ouch.
just outrageous.
Good Lord. It's a bit morbid. Bit morbid. Do we have everybody back? I think so. 1, 2, 3, 4, 5. Yep. We're missing one. Oh, okay. I suppose.
I think so. Yeah, she's like a very like spontaneous.
Well, it's like, have you had?
Yeah.
Okay, let's make a start. You know, that's sort of, we've got one patient sort of eliminated from the trial, and yes, Excel, great. Everybody has it. Can do absolutely amazing things, but it has a bit of limitations. And I believe that, and I'm looking to Helen, that if you do your data analysis in Excel, your sponsors and the regulators will probably say, nice try. You know, come back again when you have grown up a bit with your data analysis.
They'll be quite that polite.
You know, I don't want to piss off people, but as I said, Excel can do a lot of things. One thing that we've discussed today, logistic regression, where you do this classification, you know, are you obese, are you not obese? Excel can't do. That's not an option. And unless you write sort of Visual Basic things, programs, Excel is also very sort of static. You can't modify it easily unless you mess around with Microsoft stuff, and you don't want to do that, trust me. So what do you use? Well, all regulators ask for data to be analyzed in Stata, right? Or no, not Stata, SAS.
I don't think it's a regulatory requirement, but I think most statisticians use SAS. The requirement is for them to be converted into what's called ADAM or DTM databases.
Okay.
That is the extent of my knowledge on the
Okay.
subject.
Okay. And now in preparation of this, summer school, I had a chat with some data analysts who do the hard craft that you are learning at the moment. And I said to him, SAS, and he said, yes, unfortunately, it's a total pain in the proverbial. And any decent statistician would rather prefer a software called R, just the letter R. And R is a programming language as well as some statistical analysis software. It's free. I have put up a QR code if you are interested in how to set up and run R. It is not as, I would say, not as user-friendly as Excel, where you just plonk in data, but how shall I phrase that? I am almost prepared to bet the life of my born children that there is probably not a single statistics problem that you might encounter that R can't cope with. And I think that is absolutely brilliant. Does the code work? Yeah. So it should send you to, I think it's a GitHub page, where there is how you install R, and there is also sort of an interface which is called RStudio. You need to install R first and then RStudio, because then you can use RStudio for all sorts of things. You can actually even use R to paint pictures, if you like. Yeah, so it's not just statistical software. And it comes a little bit with a health warning. The warning is it can be quite addictive. Yeah. My wife has complained that she is an R widow because once you got the bug, you got the bug. You just, and when it doesn't work, you think, what the hell? Why? Why is it not working? What am I doing wrong? Things like that. It runs on Mac, runs on Windows, absolutely no problem. Runs on a crappy laptop, although sometimes it might complain a little bit when the calculation is a little bit more advanced. There is, if you've got an iPad, there is even a sort of bit of it's an app where you can run it, and I show you. It's not great, but for demonstration purposes, it's okay. So, introduction to R. What does it look like? It uses basically text files. So if you like, you can write your code in a simple text editor, and you just add .r at the end, and then R knows, yes, that's a file that I should work with. And it has a bit of a weird syntax. You need to get used to it if you want to play with that. So I've got an example here. Yes. So this is basically the first line of this script, an R script. You can add comments. You can write whatever you want, and R will ignore it if you have, in the first place, this hash symbol. So hash, and then you can write a comment. And it's always a good idea to write lots and lots of comments, because otherwise you suffer from the programmer's curse. Programmer's curse is you write a program and you say, only God and I know what this program is doing, what this line in the program is doing. And 2 weeks later, you look at the program and you think, okay, only God knows what this line is doing, because I have forgotten what this is supposed to do. So always put lots of comments for you to remember, yeah, we need to do something here, or this is what it does. Now, R is fairly small in the first place. That's why it's running on a crappy laptop. But it has sort of additional modules. They're called packages. And these packages you can download from a repository. Now, RStudio has a sort of a tab where you can say, get me this particular package. You need to know what the name of the package is. And then it will download it, install it, all good, and you can use it. But initially, R doesn't come with these packages. So you have to tell R, please be so nice and download this package. So this is what we would say in the first place, download the package. So for example, we need the package ggplot2. ggplot2 is a graphical package that generates plots, nice plots. Yeah. And then also load the package so that it is available for the program. And that is with the command library. So you just simply download the package and then say library ggplot2, and the package will be available for R should it need it for the analysis. Okay, so next one, we define the data. So we put in our data set, if you like. So here I have taken some measurements. I think they were some weights or something like that in kilogram. 1, 2, 3, 4, 5, 6, 7, 8 data points. I've just made up something. And the way you can copy paste things, there are lots of ways you can get data into R. You can even use an Excel file or a comma separated variables from an Excel file table or something like that. And with the right command, R will read this file and import it so that it is available. You then need to declare that and say, I want to give the data a name. And you do that, you give it a name. I call it here very imaginatively data. You can call it Pink Panther or something like that, whatever you want. But you have to make sure that it follows certain criteria. It has to be one word. This is called a variable. And the variable has to be one word. You can do that with, for example, underscores or dash or something like that. And so we know that the data are called data now. I could have called it, Peter, if I wanted to. And if I want to have all the data together, like in this form, I tell R that the data should be together. This is with this lowercase c, which means concatenate, put them all together. Everything that is in this bracket, that is our data set, right? Now, every single programming language that I know of would use the equal sign. So data equals, and then, you know, your data, whatever. You can do it in R, but it is frowned upon. I think they are all snobs. And if you don't want to out yourself as somebody who is totally ignorant, you use this backwards assignment operator, which is sort of the smaller sign and a dash. It means these concatenated data are assigned the name data. That is what the first line basically says. If you forget any of these things, I will probably throw an error and say, I have absolutely no idea what you mean. I can't do it. And that shows up in the console. Nice error message, and it tells you that's in line something, something, something. Yeah? Okay, now you can do some basic statistics. Here I have in the next, I have my comment, tells me we are doing basic statistics. Can you figure out what this line will do? What will that do? Absolutely right. It counts how many data points there are. And for that purpose, it has some built-in functions. So we call whatever the output will be, we call that count. And the function is length. And then we say that was our variable from here. So length of data. And it should ideally, then when we run the script, should say, well, count is 8 at the end. Yeah, pretty simple. How do you know these commands? Well, how do you know that it's length? Well, that's the beauty about R. It has a fantastic sort of help. Huge community, but also when you have more complex functions, you just put into the console, into the terminal that you use, you just put in length question mark, and it will tell you exactly what it wants in this case. Yeah, how it wants to calculate something, which parameters it needs, and so on and so forth. Okay, here we have the next one. So here we've got mean underscore val. I've just called that mean value. I could have written value, but you see, it is one word with this underscore in it. If I leave this underscore out and just have two separate words, mean val, I would not know what to do with it. I would say, master, sorry, can't do. And all I need to do is say mean val. I use the mean function of data, and it will calculate the mean. No faffing around. Can do the median. Median. I can calculate the variance. Variance. No problem. Actually, we will talk about this kind of variance. This is not var p, what R does. It doesn't know var p that I showed you in Excel. It only knows var s. And we will discuss this difference tomorrow. Standard deviation, again, you see I've got two words, but they are combined. Just simply SD data. Bingo, sorted. And I can print the results. Here I've got sort of the, again, sort of text concatenation, cat. I don't think you have a command dog in R, but cat means put text together, and you can say, you know, I want it nicely with some comments. So here count, and then you put the variable count that we've done up here. Here was our variable count. We put that in and say count. Here's the variable. It's not in these quotation marks. Anything in quotation marks is treated as text, but we want the variable, so it's not in quotation marks, and then we want a line break. And then we want the next cut, we want the mean, here, mean value, and in quotation mark, next, and it goes to the next line. It's, in a way, if you think about it, if you get used to it, it's really straightforward and simple. Wouldn't that be cool on your CV? Say you have programming experience in R. I think that's not too bad. Okay. We can also write the data into a table. Tables in R are called data frames. And that's simply this thing here. And we can then also plot the data. And so, for example, here, create a ggplot2, a plot, that's my comment, a box plot with overlaid alignment of the data so that I see what the data look like. And that's a little bit more complex, these plots, but once you get used to it, it's, you know, you don't think about it. Actually, I probably shouldn't tell you that. So again, that's why not. Hey, you know, I'm going to kill you after the program anyway, so my secret is safe. How many people are using ChatGPT? Hands up for whatever. Only about 50%, right? Or the rest doesn't want to say, right? I would suggest to you, even those who don't want to admit or who say, oh my God, that is witchcraft or something like that, give it a go. Because ChatGPT is bloody good at writing R scripts. Yeah? So you just simply say, please. I always say please. I don't know why, but I always say thank you as well. I know, it's stupid, right? But, you know, and surely an AI has feelings, right? I don't want to offend them. And if they take over the world, you know, I'm in their good books. I have a friend. I always say please and thank you, right? Say, please write an R script that calculates basic statistics from a given data set. And then before you even put the full stop in, it will start writing the R script. And there's a good chance that it actually works. How cool is that? We don't need any programmers anymore because you can do that with ChatGPT. So let's have a look. Here is a little sort of program or an app on my iPad. As I said, it's a sort of a workaround, and it doesn't have a lot of libraries included. But luckily, the ggplot2 library is included in the iPad version. And I can show you how this actually works. So here's exactly what I showed you, this program. And let's click run. Hey, look at that. What we've got is, we said it has 8 data points, right? We counted that just to make sure. Always a good idea. Always check. Never trust ChatGPT. Never trust R. I always ask it sort of questions that I can easily check. So count 8, yes. The mean is 58, median, variance, standard deviation, beautifully. Just like that. And if you've got large data sets, you don't want to do that by hand or then import it into Excel or something like that. Well, you can import it into Excel, but if you've got your data already as a sort of comma-separated variables or something like that in a spreadsheet, you just simply import that into R, and you ask it, can you please do a nice box plot for me? Or can you do a histogram? Or can you do a bar plot? Something like that. And here, in this case, it does the box plot. And I've asked it also to indicate what the data points are so that I can check. Have you missed anything? No, you haven't missed. I can see 8 red dots. Does it have any outliers? No, it doesn't have any outliers because the outliers would be marked with an X. Job done. You can actually then take this either as a screenshot, or ggplot will open it in a different window, and you can say export it please as an image or as a PDF and put that in your report. Job done. How cool is that, hey? Are you willing to give it a go? It's good fun. And unless you do some really weird stuff, you won't blow up your computer. Yes, you can try, for example, like with any other programming language, when you have, for example, a loop and you forget to close that loop, yes, then it will loop around. It goes totally loopy. And in all eternity, because the loop is not closed, and the only thing that you can do is pull the plug, because otherwise computer is just, it's losing it. So it can happen in R as well, because it's a programming language. Don't try it. I know what I'm talking about. But otherwise, it's really cool. And if you can say that you've got experience in R, it enhances your employability. Would you agree? Yeah? R is cool.
Especially in operations, no one's going to have a clue what you're on about.
Yeah, you can impress people. You can say, oh, I've downloaded the metaphor package, and we've done this beautiful meta-analysis. We use these parameters, and they all sit there and think, whoa. Sorry?
If you put it on dark mode, then I bet you look like a hacker as well.
Oh yeah, absolutely. But you need a hoodie then. Yeah, exactly. Exactly. Okay, so that's basically all I wanted to do with you today. Any questions? When is dinner? It's the most important one. Well, thank you very much. Tomorrow we are then moving on from these descriptive or from the explorative data analysis, and we will, terminology alert, we will go a little bit deeper into statistical concepts. Today we looked at what our data look like. Tomorrow we look at the wider picture. Okay, happy with that? Fantastic. See you tomorrow at 10 o'clock, I think. Here. Bright-eyed and bushy-tailed. Have a lovely evening. Thank you very much.